All right, so we know the graphs of sine and cosine. We know how to model some things with sine and cosine and how to transform sine and cosine and all that kind of stuff. So what we're going to do now is take a look at tangent and then cotangent. If we can figure out tangent, we should be able to figure out cotangent. And then we'll look at secant and cosecant as well. And then we'll talk briefly about some transformations, but those transformations are going to essentially act the same. We're not going to do near as much modeling with these functions. Sine and cosine are the main ones to use for modeling because they have that nice wavy oscillating behavior, and you'll see that there's some kind of buggy things happening with these functions that's going to make that a little bit harder for us to deal with. So let's get going. Let's take a look at our tangent and then cotangent functions. So first, the tangent function. We know tangent is sine over cosine. We've already seen that the period is pi because, remember, oops, that's not what I want. This one. We had the same kind of behavior in these other quadrants. So like this quadrant and this quadrant were the same, and this quadrant and this quadrant were the same. Because in this quadrant and this quadrant, the sine, positive, negative, of the sine and cosine functions were both the same, and these ones, they're both opposite. So our tangent function has this weird shortened period of pi. We also know there's going to be a vertical asymptote whenever we divide by 0 here. So that's whenever cosine of x is equal to 0. So we'll have to think about where cosine is equal to 0, and that should work out pretty nicely for us. Our domain then is going to be all the real numbers except for where cosine is equal to 0. Our range, this one's kind of tricky. It's going to be all real values. Basically, you can take numbers between -1 and 1 for sine and -1 and 1 for cosine, and you can get anything out of that. You can divide by really small stuff to get really big stuff, and you can divide by, you can put small stuff on the top to get big stuff on the bottom. It's kind of a weird thing. Our x-intercepts are going to be when the top is equal to 0, so our sine function. And then we'll also notice some other points. But first, let's go ahead and actually write out these things here. So we got to think, when is the cosine function equal to 0? Well, cosine looks like this. Our normal cosine function, our kind of first picture of the period looks like that. So there's a point here and a point there where they equal 0. This is at 0 and this is at 2 pi. So we know this is in the middle at pi. So this is at pi over 2 and 3 pi over 2. And then it's going to keep going, and so we can say these are really all of the odd pi over 2's, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc., 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 and negative as well. That's going to be the same thing for our domain. We're going to skip all those values. For sine, our sine function looks like this, our normal one. So there's kind of our one period pick. And it's going to equal 0 there, there, and there. So our x-intercepts are going to be at 0, pi, 2 pi, etc. Or what we can really say is all the multiples of pi. If we go back to over this one, we said these were the odd pi over 2's. These are really the even pi over 2's, right? 0 pi over 2, 2 pi over 2, 4 pi over 2, etc., etc., etc. So that's something that we'll keep an eye on. And then we also have that sine of pi over 4 and cosine of pi over 4 are both root 2 over 2, or 1 over root 2 if you wanted. And so we know that tangent of pi over 4 has to equal 1. And that's going to happen at this one, but then also at this angle down here. That's pi over 4, 3 pi over 4, 5 pi over 4. So at 5 pi over 4, it's going to happen as well. And we'll have a couple other things happening in there too. So these points at 3 pi over 4 and 7 pi over 4, these are when the signs are opposite. And so what we might notice, maybe I'll just write it here, is that tangent of 3 pi over 4 is going to be -1. Because one of these is going to be root 2 over 2, and the other one's going to be negative root 2 over 2. So this is all the information that we need to know about our tangent function. So let's go ahead and do that. I'm going to use gray lines to draw in some vertical asymptotes. So I said my vertical asymptotes were when cosine of x is equal to 0, and we said that's all the odd multiples of pi over 2. So maybe I'll just write some of this stuff down. So my vertical asymptotes are at odd multiples of pi over 2. So I need my gray color, I need my straight line. So there looks like it's pi over 2. Oh, sorry, right here. That's a vertical asymptote. That's a vertical asymptote. Oh, I'm drawing them pretty poorly. That's a vertical asymptote. These are not straight, but that's okay. There's another one at negative pi over 2. There's another one at 3 pi over 2. Or negative 3 pi over 2, and at negative 5 pi over 2. Now you'll notice the distance between here is pi, which makes sense because we said the period of this function is pi. So once we know one of those things, we can just kind of keep going from there. So we've got these odd multiples of pi over 2 for our vertical asymptotes. Our x-intercepts. I'm doing this in gray apparently. Our x-intercepts are at even multiples of pi over 2. Or really, we'll just say multiples of pi. Because 2 pi over 2 is really just pi. 4 pi over 2 is really just 2 pi. So we've got x-intercepts at 0, at pi, at 2 pi, at negative pi, at negative 2 pi, etc., etc., etc. Then we have these 2 points to think about. Tangent of pi over 4 is 1. So pi over 4 is right here. Bang. And then we could say tangent of 3 pi over 4 is negative 1. That's this one here. Or what we could do is say tangent of negative pi over 4 is negative 1. Same thing. So I think that's a really helpful kind of thing to notice. So here's a better picture of it. And there's our 3 points. Our 3 points here are 0, 0, pi over 4, 1, negative pi over 4, negative 1. And there's all these vertical asymptotes in here. So once you know these 3 points, you can just repeat this because, again, we know that the period is pi, so they're just going to get repeated over and over and over again, this same little picture. And if we connect these points and go to these vertical asymptotes, this is what this is going to look like. So we have some interesting properties here. You can see now the odd symmetry of our tangent function that we had talked about earlier. So that's kind of nice. There's this neat little odd symmetry that we have going on. Cool. Let's do the same thing for cotangent. I'm going to let you go through this in the same way that I did the tangent function. Think about where those vertical asymptotes are. Think about where the x-intercepts are, all that kind of stuff, and I'll let you go from there. So pause the video, see if you can fill this stuff out, and you'll notice the next slide is the blank graph. So see if you can kind of graph some of that stuff. Go. All right, let me check what colors I used above. Cosine was blue. I'm going to do the same thing. So if cosine is my blue one here, then my vertical asymptotes are going to be the red one now for sine. So we said that sine was 0 at all of the multiples of pi, right? Or even multiples of pi over 2. So this is going to be at 0, pi, 2 pi, etc. For our x-intercepts, these are going to be the odd multiples of pi over 2. So this is going to be pi over 2, 3 pi over 2, 5 pi over 2, etc., etc., etc. And then we still have that sine of pi over 4 and cosine of pi over 4, the same thing. So cotangent of pi over 4 is still 1. And also we'll say cotangent of negative pi over 4 is negative 1. Or cotangent of 3 pi over 4 is negative 1. Is that right? No, I think I might be mixing something up. No, I'm still okay. I think I'm all right. Yeah. Okay, cool. So we'll go ahead and we'll graph this stuff and see how we get it. So hopefully you'll end up with something like this. Perfect. So there's my pi over 4, and there's my 3 pi over 4. And you'll notice the negative pi over 4 still has this point here, but we don't use these 3 points for the tangent because 0 is actually a vertical asymptote instead of this x-intercept that we had for the tangent function. So you can use these 3 points put together, and you get the exact same kind of thing. Notice that we still have some cool symmetry going on, all that kind of stuff. Our x-intercepts are still right where we think they're supposed to be. Our vertical asymptotes are right where we think they're supposed to be. Everything works out really nicely there. Cosecant and secant. So we'll start with the secant function. Secant is 1 over cosine. So notice for this one, I'm just going to point this right out off the bat. Our numerator can never be 0. What that means is that there's no x-intercepts on this. We still have vertical asymptotes when the cosine function is equal to 0. So if you remember, this is, I think I used blue for cosine, all the odd pi over 2 multiples. Our range on this is really weird here. We can't get anything too small. Because cosine can't get really, really big, we can't get anything that's really, really small. Our period on this thing is actually going to be 2 pi because that's the period of our cosine function. So we'll keep an eye out for that. And then we have some interesting points here. Cosine of 0 is equal to 1. And so that means secant of 0 is going to be 1 over cosine of 0. So it's 1 over 1. So really you can say, all right, that's really 1 over 1. Cosine of pi over 3 is a half. So that's supposed to be secant. So I'll change that in the notes. Secant of pi over 3 is going to be the reciprocal of that, 1 over a half, which is 2. So we've got some points that we can plot. So go ahead and do that. See if you can plot some points, and everything should work out really nicely. So this is what I've got. So here are my points. This right here is pi over 3, and then you'll notice I went ahead and I just grabbed the negative pi over 3 as well, because I know I have this nice even symmetry on here. And then we know at 0 cosine is 1, so the reciprocal secant is also going to be 1. Then we have this kind of flipping back and forth business going on here because our cosine function ends up getting into the negative side of things over here, and so does our secant function, because cosine looks like this. When it's negative here, our reciprocals are also going to be negative. Now, it really doesn't go that low. Let me figure it out. There we go. There. So this is what our cosine function normally would look like. I had to squish it down to fit that scaling on here. And so the reciprocal of this thing is the green function that we've got. So notice, again, it's negative over here because we had that negative cosine values. For the cosecant function, you can pretty much do the same thing, except by this point, hopefully you'll recognize that, like, hey, if we're using sine, that means that we've got just the regular multiples of pi here for our vertical asymptotes, because that's the spot that's in the denominator. And so now we know sine of pi over 6 is a half, and so cosecant of pi over 6 is 2. Sine of pi over 2 is 1, so cosecant of pi over 2 is also 1, and then we can kind of build them out from there. So again, you can plot a couple of points on this thing, and this is what you should get. So this is pi over 6. There's a negative pi over 6 right here if you want, with this point. And this one here is 5 pi over 6. So it's like the negative pi over 6 from pi, right? We go backwards a pi over 6 value. So these are our points. And then again, our sine function starts at 0, it goes positive. So our sine function looks like this, comes back down through 0. So that's where our vertical asymptote is on the cosecant function, hits here, etc., etc., etc. When sine goes negative, the cosecant function goes negative as well. Here we have that nice, oops, I want this one still. We have this nice odd symmetry because the sine function is odd symmetric, and so is cosecant. What about transformations? Well, you can do all the same stuff with transformations. In one sense, they're easier here because we've got some familiarity with transformations of trig functions. In another sense, they're a little harder here because these 4 functions, I think, are just a little bit less intuitive to work with. You've probably worked with sine and cosine before, so we're not going to do a lot of modeling with these 4 because we just don't have the intuition behind it yet. But we can still do these transformations. So you can treat all these functions separately, but there's still going to be a bunch of similarities. Phase shifts are going to move stuff left and right. So what I'll look for is, instead of looking for x-intercepts, just move the vertical asymptotes left and right. Changing the period changes the space between the asymptotes. So that's a huge thing. Amplitude we don't really talk about because amplitude really is kind of a sine and cosine specific thing, but we can still stretch these functions. What it's going to do is it's going to stretch those known points up and down. So with the tangent and cotangent ones, remember we had those 3 points. Let me go back. These 3 points here, it's going to stretch these up and down where they're not at a y value of 1 and negative 1. They'll be at whatever we stretch it by. And for the secant and cosecant ones, this kind of middle spot isn't going to necessarily be at 1, and this one won't be at 2. They'll be stretched as well. So it's a little bit tricky to keep track of all these things. And then for each of the functions, we can use the asymptotes and then those 3 known points to build our graph. So here's an example. Take a bit to graph this. I want to kind of write out some stuff on here just to give you some hints to get started, and then I'll let you go from there. So we're going to do a vertical stretch times a half. Sometimes people will say we're like compressing this, or we're squishing this, or it's a shrink or something like that. It's not really stretching it vertically, it's compressing this thing. And then we also have a phase shift right by pi over 4. So that means for the cotangent function, our asymptotes are going to get shifted by pi over 4. So instead of our asymptotes, let me go here, our vertical asymptotes are going from 0 to pi over 4. And then the other one was at pi. And we're going to shift that by pi over 4. So that's going to be 3 pi over 4, etc., etc. Oh, no, sorry. That's going to be 5 pi over 4. That's what I wanted. Etc., etc., etc. So you can kind of get an idea for where your vertical asymptotes are by doing that. Give that a shot. See what you can do. And when you come back, I should have this graphed. So I'm just putting the finishing touches on this. But this is approximately what this could look like. So I only drew 2 pieces of that cotangent function, but oh well. You could keep filling them in because it just keeps repeating. The main thing is we've shifted these vertical asymptotes over by pi over 4, and then that period is still pi. So notice this distance is still just pi units each time. Then I know my cotangent function is the decreasing one. So it's going to drop down this way. It's going to cross through right in the middle. And then it's going to be scaled by a half. So instead of having the y values at 1, I drop them down to half and negative half here. And then I did the same thing for this one, and you could keep repeating that picture. So hopefully that's what you've got. Double check that with the stuff that you've got, and hopefully that looks right. All right, the next one. 2 secant of 2x. So here we've got a stretch. Oops, one sec. There we go. We've got a stretch vertically times 2, which means that when we have those weird little parabola looking things, the bottom is going to be at 2 and the top is going to be at negative 2. And then instead of our other ones, so maybe I'll do this, those y values, those 3 y values that went 2, 1, 2, those are now going to be 4, 2, 4. So let me go back and I'll show you what I mean by that. So here, I want the secant one, same thing. See these y values of these points, 2, 1, and 2? Those are now going to get switched to 4, 2, and 4. We're going to stretch those things up. So that's this part right here with that vertical stretch. And then this one, we've got also a horizontal shrink, I guess you could call it, or it's a stretch, but we're going to be multiplying by the reciprocal times half. So that's going to change our period of these things. Our period normally was 2 pi, so now our period is going to be pi, or really what I'm going to say is the space between the vertical asymptotes. It used to be pi, now it's going to be pi over 2. So the asymptotes are still in the normal position for the secant function. The asymptotes aren't going to be in the normal position anymore for the secant function. We're going to have to compress these things in quite a bit. So that's going to be something that we'll look at. And then those y values are also going to get bumped up. Our asymptotes used to be at negative pi over 2 and pi over 2. So now what they're going to do is they're going to be at negative pi over 4 right here, and pi over 4. So the space in between these is pi over 2. And then I'll have another one here, and then another one here, and these are all diagonal. Let me see if I can draw these a bit straighter. Oh, that's even worse. All right, let me see if I can get this. For whatever reason, I'm struggling with this today. There. And I'll do another one. Well, that one was pretty good. Yeah, all right. I should do them on this side, too, on the negative side. That one wasn't good at all. That one was okay. All right, there. Cool. So there's my horizontal stretch, I guess you could say, or shrink. We've shrunk all this stuff in. Now we're going to do this nice vertical stretch. Each of these are going to have points right here. Oops, I want to get rid of this. There. Right there. And there. And there. These points normally would have been at pi over 6. Oh, wait. Let's double check this one. I think I'm mixing this one up. Yeah, okay, I'm mixing this one up with the cosecant one. This would normally be at negative pi over 3 and pi over 3. Since we're compressing it, now it's at pi over 6 here. So that's negative pi over 6, and that's pi over 6. So this is what one piece looks like. The next piece is going to look the same, except it's going to be upside down. Oops, that's not negative 4. There. And then we're going to have one that bounces back up here. Point there, and there. And we can keep connecting these things this way. Cool. And then we could keep going in between these asymptotes. So we're going to have something that looks like this again. And then something that looks like this again. And so that'll be our secant function, 2 secant 2x. A little tricky. Absolutely feel free to use some technology to double check all this stuff. Get used to your graphing calculators. Play with the windows on here. You can go into the zoom menu and hit trig, and it'll give you a nice trig scaling where the tick marks are at reasonable values. But feel free to use the internet. Wolfram Alpha, GeoGebra, Desmos is a really nice one. Desmos, let me write that down. Probably put this on Canvas somewhere too. Desmos is a nice graphing calculator online that would help you graph these functions really well. So keep an eye on that kind of stuff. That's all we've got for these. There's no real applications of these functions that we're going to talk about because they don't have as nice that smooth kind of oscillating back and forth behavior. We have this weird kind of bouncing around with asymptotes and strange things going on. Cool. If you've got any questions, shoot me a message on Canvas, post in the discussion boards, let me know.